Hello everyone, my name is Marie Correcla and welcome to today's AIRAH Technology Talk webinar session. I hope everyone's having a good week so far. So today's Technology Talk presentation is presented to you by LAROS Technologies. And today's presentation will give you a bit of an overview of how building airtightness and mechanical ventilation are tied together, with discussion on how building airtightness is specified and tested. Just before we get the session underway, as always, if you've got any questions, please pop them into the Q&A box that's located at the bottom of your screen. And in today's session, we will be allowing some time throughout the presentation and also at the conclusion of the presentation to go through any questions you may have. So I'd now like to introduce to you our presenter for today. So we've got James D. Salis, who is the General Manager of LAROS. And James will be taking us through today's session. So James, when you're ready, I'll hand things over to you.
Today I'm going to be talking about the link between airtightness and ventilation and how those two should always be considered together. And unfortunately, at the moment, they're not. So I work for LAROS Technologies. I'm actually the general manager and the head of the engineering team at LAROS. LAROS is is one of the suppliers of ventilation, facades, windows, external shading, thermal breaks, and other product lines specifically for high performance building, particularly when it comes to more airtight buildings or buildings that need a little bit more consideration in terms of the high energy performance, potentially resulting in more tricky detailing. We try and provide an entire package of those solutions and products, and of course the engineering to go along with it for the product lines that higher performance buildings need to achieve those better performance outcomes, particularly with regards to airtightness and ventilation, which I'll be focusing on today. So I'm going to be talking a little bit about how we define the building airtightness, how it's tested as well. Also changes in the construction code, which you may or may not be across. There has been a few changes in the last round, and then of course some in the draft round potentially. Then how the airtightness is achieved in practice, and then some standards as well. And then of course moving on to ventilation, which potentially a few of you are more familiar with. Talking to a bunch of mechanical engineers, you should all be pretty across the ventilation requirements, but then potentially how they're linked and how you can join them together in practice as well. So then retrofitting options for ventilation systems. So the first thing to get across right up front is that there's two different terms I'm going to use, infiltration or air leakage, and ventilation or controlled mechanical ventilation. So air leakage is defined as uncontrolled leakage through the building envelope. You can see in the image there on the left that it can come through building envelopes in all locations. It does have more prevalence in detached housing because there's more surface area to the outside for each of the occupancy units, but it does occur in all classes of buildings, and it depends entirely on how the external envelope goes together. It's also defined in terms of air changes per hour or permeability, much like the mechanical ventilation is also sometimes used in terms of air changes per hour. Those two words are interchangeable in that the amount of volume leaking through the building is defined in the number of times that volume leaks out every hour. But in one case, it is controlled and forced by a fan. In the other case, it can happen depending on wind loads, conditions, and also the occupants. The middle shows a window, which is probably one of the more contentious parts of mechanical of ventilation design. It's not controlled ventilation in that you have to rely on the tenant or a occupant to operate those devices. And also it depends entirely on outside conditions as to how effective that unit is. So for the purposes of this presentation, windows are either not considered or are essentially ignored. At the moment, the building code does mention airtightness. It doesn't put up much of a challenge in that front. This is the 2019 building code showing that a building has to be put together in such a way that everything is close fitting. Your internal window frames, door frames have to meet the walls and doors. They have to have self-closing dampers on your extraction fans, and it has to be put together in a way that minimizes air leakage and is well sealed. But there's no quantification or numbers associated with that testing or the performance of the building. What did change? There was some additional things put in here in the 2019 building code with regards to airtightness testing, permeability of 5 or 10, which I'll go into permeability in a bit, depending on what building and what climate zone was used. But unfortunately, it was only put in there as a verification. So if a test was conducted, you had to achieve a certain number. And that has seen a lot of growth in the airtightness testing and verification industry. However, it also potentially put a bit of a rocket up our backsides with the blower-door testing community, because we realized that if it was to be implemented in every single building with the building code, we weren't ready. So now there's been a lot of emphasis on increasing the amount of blower-door testers, the training of those blower-door testers, and the education of the building community at large. So potentially the energy efficiency section and the condensation section may have, they're in draft mode at the moment, may have more to say about airtightness. And the reason that they're in the building code is that the airtightness of the building has a huge influence on the performance of the building. When you have a small gap in the insulation, like I've shown here, the thermal performance of the insulation can go down by a factor of nearly 5. So this is some fairly harsh conditions inside and outside. It would be a little bit better, of course, in a lot of places, but Canberra does get down to those -7s and -5s. So a lot of Australia needs to consider this. Essentially, you lose most of your insulation value if there's wind blowing through your insulation. And even worse is the amount of moisture that flows through a gap like this. Diffusion is quite a powerful force. And if you have a sealed piece of plasterboard, you get about 0.5 gram diffusing through the plasterboard into the insulation. If you have a 1 millimeter wide gap, then you get about 800 grams. That's almost a litre of moisture being diffused into the insulation, which can provide some pretty healthy growth conditions in that wall structure for mold and other potential structural damage, even from condensation forming in that wall. This is a more recent, this one was from 1989. So this is not a new problem. This is a more recent study showing that if you have a wind barrier installed, so no wind barrier there in the top right, or a poor wind barrier, which I think was the building code at the time they did this study, that the insulation values are dropping from somewhere in the realm of 4 and R4 insulation value. And this is under a very moderate wind of about 10 to 15 kilometers per hour, is that purple line there, that the wind is stripping away up to 90% of the insulation value. So your R value from inside to outside is dropping by 90%, which is a lot of money lost when there's a slight breeze outside. So really, we need to focus on how to achieve airtightness. And again, this might be new to some of you, but it's based on essentially the use of various construction types, tapes, silicons, expansion foam, various building wraps and other materials that are airtight and can be used as an airtightness layer. And then, of course, fire compartments. Fire compartments have to be smoke-proof, and as an extension of that, they're usually quite airtight as well. So penetrations, preparation of those penetrations, various products are available to achieve that. But the most important thing is to decide where the line is in the first place. So there's a thing called the red pen test. Essentially, you can draw a line around the building. Either this is done by the ESD team or potentially by the mechanical systems team as well, deciding where is inside and where is outside. And then, of course, once you know where the line is, you can then define how you seal that up. That can be done with a building wrap. This is a more common way of doing things in very high performance buildings where you're aiming for an exceptionally airtight target. You can use an internal building wrap, or you can use the internal plasterboard or internal fittings of other description, say the internal fit out of a firewall, for example, fire check or something like that. It does require additional detailing around the internal airtightness cavity. And of course, a lot of additional detailing when you have mechanical plants. So this was a project here in Canberra where we had a lot of penetrations through a building that had to be quite airtight, an airtightness level of 1, which was quite impressive. And that was mostly done with building wraps and tapes, but also some consideration in the fire sealing as well. So that is usually fairly airtight. Of course, it has to be to stop smoke. How do we measure the airtightness? So once you've got a number that you've put in your specifications, you achieve the airtightness by pulling the air out of the building. This is a good graphic from Proclima, one of the suppliers of building airtightness materials. They have essentially the process for blower door testing is to pull the air out of the building and then see where it leaks in and measure that amount of leakage. So once you've measured that airflow at a certain pressure, you can use a whole bunch of equations. Usually it's done by a computer where you can work out the air change rate, the permeability, potentially the specific leakage rate or the effective leakage area, and then give yourself a value that you can compare from building to building. And that's the key here, is that we want to be able to compare two buildings that are very different in size and shape, but still testing the envelope in a comparable way. This is a great report from AIRAH back in 2017, and the air tightness metrics used. It's basically a long-winded way of saying that permeability is the easiest way to compare buildings because the air leakage through the building is easier to define in terms of how much surface area or air leakage is going through the surface area rather than the air leakage in terms of the volume of the building. If you use the volume, then it becomes quite easy for very large buildings and very hard for very small buildings. But really, you're testing the envelope, so you need to use a definition related to the envelope. And how you test it, you put a big fan, like I said in the other slide, put a big fan in a doorway and pull the air out. Here's some photos from Efficiency Matrix down in Melbourne. We do our own blower door testing here in Canberra as well. And there's a couple of other people with large fan kits. And so you can set these fans up in a doorway, pull all the air out of the building and measure the leakage through the fan to get you that air leakage rate. Some typical air tightness levels that you may encounter, or that to give you an idea of how airtight everything is at the moment. High-rise or larger buildings, usually dominated by the glass facades, which are, of course, very airtight. They have pretty set air tightness levels that are achieved at higher wind pressures, for example, than the blower door testing. And so the blower door testing achieves an excellent result when you pull on those buildings. The important thing to consider is the mechanical penetrations in those large and the lift shafts in those large facades buildings. It can be quite tricky whether you're excluding that or including that. It depends on the project, but you need to think about it early on. And then as your buildings get smaller, medium rise is usually fairly airtight as well, because you have a precast concrete and glass system. Precast concrete is inherently quite airtight. And then as you go down to the low rise and the single dwellings, you end up with a much leakier process, often because the fire compartments and fire considerations are less, but also because there's a lot of various facade materials that are meeting, be they brick veneer or metal with ColourBond or other external, weatherboards and things like that, other external materials that are used, and they all have to join together, and joining them together in an airtight way can be quite tricky. One note on who's regulating this whole process. There are a few organisations active in Australia. So we have ATMA, which is the Airtightness Testing and Measurement Association. They register us and make sure that we're doing things, and they audit our tests and all of that sort of stuff to make sure that those tests are being done in a uniform way. Every test that gets done should be registered with ATMA. They can then look it up and check that you've done the test in the correct way. And then there's also the Air Infiltration and Ventilation Association of Australia, which is essentially an association of building product suppliers in terms of building wraps and airtightness in combination with ventilation system suppliers, so that we can kind of draw those two topics together. And then when you're looking at your mechanical specification, you can have a couple of standards to really go off. Generally, it's referencing 9972, but TSL 1 and 2 are actually the better ones. They're more prescriptive. If they're available online, and if you read through those, it actually tells you how a blower door test is conducted in detail. TSL 3 is for very large commercial buildings or specialised tests, and that's on a case-by-case basis. And then 4 is for passive house or other very airtight building standards as well. Alrighty, so obviously you're all a little bit more aware of the ventilation topic. Big mechanical plant pushing air around buildings to achieve a comfortable internal environment. Of course, the Bible on ventilation is 1668.2, use of ventilation and air conditioning in buildings, mechanical ventilation section. Most people do just skip straight to the appendices and read the amount of air that they have to blow through the building for various sizes. It doesn't make any reference to an airtightness level. However, section 1.2.2a does mention you have to have appropriate makeup air. Now, what appropriate makeup air is often up to the designer of the building, and that's what I want to talk about a little bit later in the presentation. But essentially the extract airflow and the supply airflow on a one-person apartment, they don't match up. So you can see there 10 litres per second is the recommended supply airflow. 25 litres per second is the recommended extract airflow. If you're putting those two numbers together in a sealed box, you end up with a pretty big discrepancy. You have either too much airflow coming through the apartment when you have the extract system running, it's more than one person needs, or you don't have enough airflow according to 1668 for the extract system. You have either too much or not enough. They don't match up. It's not balanced. We need to review that process as a whole. Of course, for larger systems, which a few of you may be more familiar with, there is a requirement for energy reclaiming system on systems that have up to over 500 or over 250 litres per second or 1,000 in benign climates. They need an energy reclaiming system, but we're talking more for multi-resi in this case. And so when you have multi-resi, those systems are very small, 25 to 50 litres per second. The code doesn't require any particular outdoor air treatment to be applied to that. It probably should, and it may in the next variation. So really we want to talk about how we should ventilate. Potentially less airflow or longer and more continuous operation. Relying on the 25 litres per second extract does give the option for intermittent ventilation, and lowering that airflow but running it for longer is generally more comfortable and having dedicated makeup air systems. So we need to remove the reliance on tenants and occupants hitting that fan switch, because it's not actually achieving good outcomes. When you have a particularly airtight building, or when you have a tenant who doesn't want to turn on the extraction fan because it freezes their apartment when it's running, then either way, the mechanical system has failed. And so it's not providing that comfortable environment. And if you're not providing that comfortable environment, there can be other issues that arise as well. So when you have an environment that's not ventilated very well and does have a person living in it, unfortunately, they breathe out a lot of moisture, breathing out CO2. There's other contaminants that need to be considered. More recently, obviously, virus particles and things like that need to be vented outside or filtered out. And so we do have a consideration of what happens in these apartments when the ventilation system has failed, like I talked about before. And this is some photos. This is one of my friends' apartments down in Melbourne, and they have metal battens and things around the place. And you can see that because the internal airtightness the internal relative humidity is rising because it's a very airtight apartment, it's actually reaching the dew point temperature around framing and around penetrations, and particularly on the windows, where the moisture will condense out of that air and then form on surfaces very easily. And we actually did an experiment, a bit of an anecdote for you. We did an experiment in this apartment. This is a fairly new apartment, been designed very nicely. It has excellent fit out, nice bench top, for example. But the ventilation system and the mechanical ventilation system relies on the tenant running the fan. And I run some rough numbers. They probably need to run that fan for 2 or 3 hours a day to achieve the airflow rate, an average airflow rate of that 25 litres per second, meaning that when you have the requirement to run the fan, you also freeze the apartment because it's pulling through at much higher than the comfortable level. The air conditioner can't keep up. So we, like I said, did an experiment, turned the aircon on and turned the extraction fan on. The windows dried out. The wall potentially didn't dry out. Not sure about the thermal bridging that was occurring in those metal frames, but that's a separate issue. But the windows dried out over 2 hours. It took 2 hours of the extraction fan running to drop the relative humidity internally from 70%, which was way too high, down to 55%. And the tenant in this apartment and the owner of the apartment refuses to do that ever again. It was freezing cold, and while the windows did dry out and the outcome was good, the mechanical system worked as designed. The as designed mechanical system was failing that particular tenant. And I know that's a standard system for most apartments. As a side note, when you see pictures of mold and things like that, you want to know whether it's likely to happen or not. So AIRAH does have DA07, which was released last year or the year before, and it has a mold growth index that can be calculated based on various internal and external relative humidities. And so there's an excellent webinar from Jesse Clark on the AIRAH webinar database as well. So you can have a look through that. But you can see there that a person releases somewhere in the realm of 6 to 7 litres per day of moisture that has to be dealt with via various continuous ventilation. Obviously, the Building Codes Board knows this is a problem and has put in provisions for changes there, meaning that we have an option potentially of, this is in the 2022 draft, for a lower airflow when operated continuously. So the apartment stays more comfortable when the continuous ventilation is in operation, or 25 litres per second when operated on demand. The same thing for a kitchen. It's dropping off quite considerably, but ensuring that the kitchen range hood, which is a source of a lot of moisture, does have to be running outside. So this is more, I guess, angled towards continuous ventilation systems where you may have a heat recovery system or something of the like running continuously at a much lower level where it's less noticeable to the tenant, less likely to that the tenant is going to try and disable it. And then allowing that to be the case will hopefully get much better outcomes where you have the ventilation being a continuous process, not relying on tenants turning the ventilation system on and off. They also have some extra things for make-up air and run-on timers as well, potentially in this draft. It may be will stay in there. There's a bit of change in the building code in 2022, so there's a bit of pushback, obviously, when you change too many things at once. But the big thing there is to ensure you have make-up air or with a door undercut or in accordance with 1668. So you have to balance your ventilation systems for every apartment as well, which is not what is currently done. Essentially, if you have an airtight building or a hot outside environment, cold outside environment, noisy, polluted, which is very common in most buildings where you have big roads outside, and the occupant won't turn the fan on, you can't rely on the window to be your ventilation system. So you have to assume that you are the tenant, or you're as a mechanical engineer, you're the protection for that apartment from mold, essentially. So we're about halfway through the presentation, and I wanted to do a little bit of a poll and answer. There's some questions popping up here as well. So I might ask if we can put a little poll in there. For the mechanical engineers in the audience, what sort of make-up air do you design into your buildings at the moment, and have you designed in the past, assuming whether the building will be super leaky, whether there's vents in the facade or make-up air through the facade, a dedicated make-up air fan perhaps, or running the make-up air fan into the AC system, resulting in a lot more comfort for the tenant, but also higher operating costs, or if you've been looking at doing energy recovery ventilation systems as well. Of course, budget is a constraint. Unfortunately, you do have budget constraints in every job. Every client, every developer, they want to look at the bottom line. And so it's important to consider that budget constraints, how to achieve these things with budget constraints being as they are. I can see some results coming in, which is great. Very, very rarely do people actually consider the airtightness of the building, which is what I'm actually seeing in these results as well. I'll also have a look, see if I can have a look at these questions. Okay, yes. So we have the question about 10 litres per second So the extract air, not per person, is 25 litres per second in the, sorry, if you can't see my screen, the question is 1668. Doesn't specify 25 litres per second per person as the extract air. No, that's right. It does have 25 litres per second as the extract per wet area or per bathroom, for example. So we have bathroom, and generally when you're talking a one bedroom apartment, it has one bathroom for one person. So I'm kind of making the equation there of 1-to-1. And the plan to deal with failures. So yes, that's the important thing. So the fans are cheap as chips. So no doubt they'll last more than a few years. And so essentially it does require, like with anything, a better maintenance schedule. And so a lot of buildings will require more consideration of the maintenance, whereas whether that's in terms of tenant or owner education, you really need to talk about the extraction fan as your mold prevention system when you're talking with people as well. So having the building with no extraction fan, it really needs to be education for the tenants, for the building owner or the occupier or the operator, sorry, that when the extraction fans fail, that's the mechanical system failing, and you have to have other considerations or checks or more maintenance performed on those buildings. Okay, let me go back into the presentation. Is there any other chats? Nope. Okay, let's have a look at the poll.
Just had a couple of questions pop in.
Oh, a couple more questions popping in. Good. Yeah, we should have a couple of minutes for questions before I get into how they link together. Yeah, so that particular study, the R value thermal insulation by a factor of 5. So the R value is actually measured by the amount of energy. When they do the R value calculations, it's by the amount of energy being put in one side and coming out the other. And what they did in that particular study, it's not, I guess, fully technically correct, but it's more realistic in terms of the performance of the building in real life, is that they did that same plate on both sides of the insulation, and then they had the air go through the insulation. And so the air going through the insulation, or well, actually from the outside into the insulation and then back out again through your air tightness leakage, was resulting in much more conduction through the structure. So the warm side was losing energy a lot faster. And so that's how the calculation is done, where your effective R value, which is important there, it's not, I guess, technically the R value of the insulation, because the air is considered separately, very sneakily by a lot of insulation suppliers, but the R value of the insulation as installed, or the effective R value, is dropping very quickly. Yeah, and then there's also a comment about the draft, and I did mention that it's a draft, and there's a lot more discussion around it. I'm really putting that in there as a less than AS 1668.2. Yes, so there are two conflicting things in there at the moment, where the lower airflow in the condensation section, or is not allowed in under 1668, because you have a lower than acceptable extraction amount. That's that 25 litres per second. It's lower than 1668. So it may have to be a performance solution, for example, or another discussion. And hopefully that is all ironed out, because it would most likely result in better outcomes. And we've got a question about average air permeability rates. So when you have average air permeability rates, it depends entirely on the type of building as well. So as I mentioned in the earlier slides, high rises and large buildings are actually exceptionally airtight when comparison to the amount of surface area, because glass facades are very airtight, meaning that you do have to really look at your makeup air systems, particularly when you're looking at glass walls and things like that. And then when you have a smaller building with more facade systems going together, then you have a much higher leakage rate. So I've done a lot of testings on smaller townhouses and things like this, and I'm seeing numbers between 5 to 7 fairly often. And so it is meeting the building code requirement of 10, but it is also resulting in bad outcomes in terms of energy consumption. Okay, a couple more coming in, which is great. Great engagement. I'm loving it. Most consultants will not exhaust 25 litres per second. Yeah, so 40 litres per second minimum in a reasonable time frame. So that's the argument that always comes back, is that the minimum will be 40 litres per second is essentially what Stephen's saying here, to achieve mold reduction and clearance of steam in a reasonable time frame. So reducing the flow down that much will not be taken up by consultants with the higher level of risk. And so when you have 40 litres per second fans running, you will often see people try and disable them or not run them at all. It's a discussion with tenants. If you ask people who live in apartments, they will not turn on a big extraction fan. A, it's really noisy. You can't sleep with it. B, it won't run when overnight or when the tenants aren't there. So they don't want to leave it on 24/7. And C, it will increase the energy consumption of that apartment by a very, very large factor. Something like 50 or 60% or more, actually, if you're pulling that much air through the apartment, you're getting high air changes. And so more airflow from a consultant perspective may be good in terms of covering your design. You designed it to meet the code, but it's not good in terms of the outcomes because people won't turn those fans on. So the range hood exhaust, yes. So I do mention that a little bit later as well, but the range hood exhaust, reducing it down to 12 litres per second continuous will not be as effective as it reduces the capture velocity. So in terms of range hood exhaust, that's not actually the range hood airflow. I interpret that as an extract system in the kitchen. And so I do talk a little bit about recirculating range hoods, how they were removed and now they're potentially coming back. They're certainly still in Class 1 buildings, used quite a lot, but the capture velocity can be quite high if you're returning the air to the room after the grease and the grease particles and everything have gone through the grease traps and then blown back into the room. As long as it's not blown back towards the tenants, they will probably still use the system, but then you need a separate extraction system to remove the humidity or the fine smoke particles. And I think that's the intention of the 12 litres per second there, is that if there's a separate extraction fan or a continuously running extraction system that's pulling air out at 12 litres per second, it will still clear the air in the room. While the higher velocity airflow, many litres per second coming through the range hood, do still direct the air through the grease traps and the filters. Again, natural ventilation. There's another question here, whether NCC DTS approach under natural ventilation, then 1662 minimums are not required. Yes, sadly, windows are not ventilation systems, but currently the architecture and the certification and a lot of the industry sees windows as ventilation systems. And that's just going to take lobbying on our behalf as people who have seen bad outcomes and design these systems, and particularly knowing how windows are not often opened, particularly in Canberra, but also in Melbourne as well, and a little bit of Western Sydney. When it gets particularly cold overnight, you're going to get windows not being opened, and so they're not a ventilation system. And yeah, comment from Joel that's come in as well. Not a, I guess, a question, but the steam clearance rate in the short term is not related to mold growth. And he's right. The mold growth is from the amount of moisture averaged over the day. And you'll find that if you have a continuous extraction system that's operating the whole day, you'll have your shower recess and your towels drying out much more effectively than if you have a large fan that you run for 20 minutes. So a very large fan pulls a plug of moist air out of the room very quickly. Obviously, the mirror doesn't steam up as much, but then you will still have a lot of moist surfaces in that room that no longer have any ventilation applied to them. And those moist surfaces will evaporate into the space. You'll get higher relative humidity, and then you get mold growth. I will have to wrap this up though. The questions still coming in. I'll probably have a look at some of them at the end. So that was a good 10-minute break. I'll get back into it and let's have a look at the poll results. So what we're seeing here, is that no makeup air design is the roughly 8% of people. Vents in the facade or into the roof cavity, then vents back into the room through the fridge. Dedicated makeup air fan, those two are pretty equal. Makeup air fan into the AC system, that seems to be the way that a lot of people are going, because it reduces that issue of cold air blowing into the apartment and making the building uncomfortable. It does still have the issues with a high energy consumption overall. Energy recovery ventilation system, that's great. A fifth of people designing with energy or heat recovery ventilation systems. Excellent. And then it depends on the budget, obviously. So it's usually one or two. The cheapest option. When you say it depends on the budget, then it's usually the cheapest option. And a few people are looking at the airtightness of the building. So that's really good to see. All right. So let's get back into it. So what we want to talk about now is the link. If the building has a known or a tested or a designed airtightness level, what sort of active ventilation should be designed? Obviously, it depends entirely on how leaky the building is. And the Air Infiltration and Ventilation Association of Australia, a bit of a mouthful there, put together a guideline document. This is non-binding, obviously, but it was done in 2020. And then, unfortunately, the world kind of shut down for 2 years. And so nothing's been done with it since. But we are trying to look at this a little bit more. So you get a little bit more design advice from ventilation and airtightness working together. So if, for example, you have a very leaky building, it's often better to have a extract-only system that is intermittent, meaning that if you have intermittent extraction, it turns on, the building will have passive leakage that unfortunately has very high energy consumption, but does have the advantage that it will dry the building out if it's heated, because you'll be driving that moisture out through those cracks and crevices, potentially resulting in other issues, but the internal environment will be healthy. When you have a less leaky building, then potentially continuous is the better option. It does depend on the crossover and the makeup of the building, but it does result in a high energy use. Whether they're extract only systems, which aren't really suitable for tropical climates, because if you're just doing extract only, it means you're pulling in humid air from outside. Supply only is another option, but obviously you have to deal with the extract system not meeting the 1668. So a balanced system is generally the better option. But of course, coming down to cost, that can be a little bit harder to get over the line. Of course, once you get into about a 2 to 6 cubic meters per square meter per hour leakage rate, then you get into a bit of a gray zone where the system does need continuous ventilation. But if you're forcing continuous ventilation with a balanced system, you can actually get leakage out through the building envelope in some rooms and leakage in through the building envelope in other rooms. So it's a little bit of a riskier zone potentially, particularly with ducted systems where you're pulling out from a bathroom and designing the system such that it pushes in through the bedrooms. You'll often get quite a bit of leakage out of the bedroom windows, and then the additional leakage into the bathroom windows, or in through the room, through the main door into the apartment access corridor or something like this. And so 2 to 6 can be a little bit trickier. And I will talk a little bit more about that when I get to decentralized systems. But if you're achieving below 2 or 3 air changes per hour, then you need continuous ventilation, and you can get really good returns with heat or energy recovery. So where your system is designed as expected, there's undercuts under the doors and everything like this to allow air to blow from one room to another in a balanced and controlled way. You will achieve the desired outcome of heavy reduction in energy use and a reduction or elimination of a buildup of internal humidity. So those two things work together. So achieving high permeability, high air tightness, low permeability will increase the good outcomes of the building. It's just getting there that's the hard part. Obviously, look at 1668, meet the code, et cetera, we haven't really looked too much into getting this out there too much. And so I do want some feedback on this. If you have a look through the document, I think it's available on the AIVAA website. If not, I'll get them to put it up. So we can have a discussion and at least get the ball rolling. It might not happen in this code, maybe not the next, but a link between the two is important. Green Star is famous for putting ventilation and air tightness in. And they say if you have a certain level of air tightness, you have to have a certain level of ventilation. Or actually, it's vice versa in this case. If you have trickle ventilators or intermittent extractors, don't make it too airtight. If you have passive, then don't make it too airtight. If you have continuous, you have to make it more airtight. But if you have continuous with heat recovery, you have to make it very airtight, as I was saying before. And obviously, those numbers are adapted from the APMA documentation as well. So here's a couple of slides. Joe Stibarek is one of the, my apologies, is one of the better lecturers over in the US. And obviously the US has had these issues a lot longer than we have. They've been building airtight. They've got colder environments. They've got pretty nasty humid environments down south as well. And so the standard build options over there, and I've adapted his slides here to show our environment. Essentially, if you're extracting from the kitchen or extracting from the bathroom and you have a mechanical plant of some description, you're relying on the permeability to be greater than 5. And if you have a standard build without a permeability of 5, you can put holes in the building to give you that outside air. And there can be situations where, for example, in that poll I mentioned, people venting into the roof cavity and then venting down behind the fridge. There can be situations where that doesn't actually achieve the desired outcome, where you have the fridge, most fridges, very efficient. They don't put out enough heat to stop or to pre-warm the air that's coming in from outside, meaning that you have a bad outcome in terms of comfort and energy consumption as well. Options on recirculation in the kitchen, but they still will need a dedicated humidity removal and smoke removal system. Then, of course, you can have dedicated outside air. A few of you put that in the poll, where you have outside air blown directly into the HVAC system, potentially with dehumidification occurring there as well, or extraction from the bathroom to balance that dedicated inside air. And then for less permeability or a more airtight building, you can have, a very efficient system of potentially interlocks or balanced heat recovery system as well. So that covers all of that. What we want to talk about a little bit is about retrofits. So there are, unfortunately, a lot of buildings already existing in Australia. And so we don't have the option of really installing these large ducted systems into a lot of buildings. So we just have to work with what we can still get to. And so the easiest is smarter extraction fans, meeting those requirements that I was talking about before, of a low basic ventilation being pulled through the building continuously, potentially with switched or humidity control boosting. There's a couple of brands available, Panasonic, Lunos. I think there's some others as well that you can get with a humidity control built in, backdraft damper. They're really quiet, so people don't notice they're running most of the time, but then they also have a boost mode. So one thing with apartment owners in particular, they want to have the ability to flick switches and have things happen. If you don't have a switch, then you lose essentially your agency, your control over your apartment, and it annoys you, and you then complain about continuous extraction systems. And I've had that discussion with quite a few people. So you still need a boost mode, and you still need the ability to pull out smells and other things as well. But from the humidity control perspective, you need to have constant low ventilation. Often there'll be requirements for an EC motor, which draw, and there should be for everything, EC motors. They draw a lot lower power at these part load conditions. AC motors become very inefficient when you run them at part load or low speed. Essentially, they're throwing away the extra energy that would have been used to spin them at full speed. And so you really want, for a part load or a dual duty fan, to have a EC fan. Better, of course, is to put a ducted ventilation system in there. These are big units. You might recognize drawings like this. If you're a mechanical engineer, you would have seen complex systems like this. A whole building has a large heat recovery system sitting on the roof and providing heat recovery to that fresh air. And that was the numbers I talked about for those large commercial buildings. And then there's also small individual occupancy units buildings as well. So you can, units for individual occupancy, and you can install those units in those environments. Run the ducting everywhere inside the apartment. And then there's a lot of options there for running fresh air into various rooms and pulling it out again. However, it's very, very hard to retrofit these systems. So we do need to look a little bit at the retrofit options, and decentralized is often the best option for that. So essentially, you're putting small heat recovery systems that run continuously at very low airflow levels, either through the through the external walls, scattered in around apartments, or ducted to just 1 or 2 rooms from the external wall as a retrofit situation. The most common version of this is a push-pull system. So in terms of a heat recovery wheel, which most of you will be aware how it works, essentially it pulls the matrix from the outgoing airstream into the incoming airstream. And when it's in the outgoing airstream, it's being warmed up by the outgoing air. And then it's essentially acting as a conveyor for warmth, where the outgoing air has its warmth harvested and put into the incoming air. The same thing happens with decentralized systems with a ceramic or a aluminium heat recovery core, but the fan changes direction rather than the heat recovery core going from different airstreams. So you can have the system running with the outgoing air, the humid warm air going out for about 90 or 120 seconds, depending on the unit, blowing through that heat recovery core, which you can see in the picture there, and then venting that cooler air outside. Then they do change direction and pull the air back into the building through that heat recovery core, and that gets preheated and blown into the building as fresh warm air. You can scatter those around external walls. These are particularly useful for retrofit, and that's why they can be installed later on in an existing building. And we're finding that very often where people have retrofit double glazed UPVC, they've sealed up around their windows, and they've had excellent air tightness and reduction in their energy bills coming very, very effectively. But then they've also had increases in condensation and moisture related issues, because those buildings, rather than knock it down and start again, they've done the good thing and used an existing shell, but they've made it more airtight, and then they've made it need more ventilation and more continuous ventilation. And that's where these units really come into their own. Essentially, these units operating in pairs, where one's pushing air into the building at the same time as one pulling air out, as you can see in that diagram there. They do also have, they work quite well in combination with those smart extraction fans, where the extraction fan potentially pulls a very small amount of air through the bathrooms, which means that these aren't as 100% balanced as they could be. Potentially 5 or 10% of the air coming in these units goes out the bathrooms. But then you do have still heat recovery tempering that air as it blows into the building. And when the bathroom fan or the kitchen range hood extraction ramps up for a very short period of time, you then get much more air pulled through these units. The heat recovery drops quite considerably, but it's still being tempered by the heat in the heat recovery core. And the reason that these, because they're so effective and they're actually really able to fit, there's a bit of a flood of them coming into the Australian market now. Lunos, Fantech, Steelotron, you can actually buy them at Bunnings. Well, you have to walk into Bunnings and pre-order them, and then they have to ask you what the hell you're talking about. But they do make this sort of system, and they do sell them at Bunnings now. So it's becoming much more mainstream because of the problems associated with this. There are other larger systems. If you don't need, or if you don't have the push-pull options, there are potentially for higher airflows, larger wall-mounted heat recovery systems, which are essentially a miniaturized version of the larger ducted systems with a supply and exhaust air duct in the same room. They go out through the wall as well, so they're easy to retrofit. You just have to core drill a hole and find some power. And then those units provide fresh air with heat recovery into that space continuously. There's a few retrofit options that we've had where the unit just gets mounted. You can see putting an air conditioner in one of these units next to it supplies you with conditioned fresh air very easily in terms of a retrofit situation. That was a very moldy room. That is not moldy anymore. Of course, classrooms are the big one. So a lot of people, due to the recent pandemic situation, have realized that having a lot of children in a closed room for a long period of time is no good. Unfortunately, that wasn't the case or wasn't considered a problem when it was CO2 related. Kids were just falling asleep in classrooms. But now that there's viruses about the place, we need to get fresh air in there as quickly as possible, which is excellent. It should have happened earlier when people were falling asleep from the CO2, but now it's happening. And so there is actually a flood of units available on the market, which are retrofit versions of those wall-mounted systems. They just have much higher airflows. And there's a couple there You can get them from various suppliers as well. We do supply quite a few of those units. All righty, so I've got about 10 minutes left. So we might get back into the question and answer. Let's see what is going on. Yes, okay, so there's a comment about 25 litres per second being the minimum in hotels, for example, because false alarms due to steam. And yes, I'm not against larger peak airflows, particularly for a hotel environment where there is no other ventilation. It's a very well sealed building. Peak airflows to reduce that steam is very important, but I wouldn't recommend running it that hard all the time. So humidity sensors or interlocked with the lights in the bathrooms, for example, something like that is the better way to go. And then ERVs obviously best, but again, they need to be able to boost. So ERVs that have a boost mode are the other option. Usually they're designed as a steady state system, as a fresh air supply. And if you have ERVs that have additional humidity sensing, then they can be a good option. But of course, cost-benefit analysis always come in that instance. Something to note when talking to architects about not considering windows as a makeup air path is that the notes and commentary on clause 3.8.1 in 1668.2 is a great referral. All right, thanks for that, Scott. Quoting that gets the architect moving towards other makeup air paths. Yes, that is correct. So 1668 is mentioned in the code a lot. It does have some good things in there, but it's a big read. And so finding out those good sections, 3.8.1, thanks for the reference, is a great referral to get people away from considering windows as mechanical ventilation systems. Vivian is saying that with large scale systems, it's well known that under a large proportion of outdoor air conditions, the heat recovery system will be consuming more energy to run than is actually recovering, thus necessitating the ability to bypass the heat recovery element. That's correct. Most good systems should have a heat recovery mode, and decentralized systems, they will have that as well, where they either operate one or operate in one direction for several hours without swapping directions as well. So you can achieve that with the decentralized systems, but most high quality ventilation systems will achieve a bypass system. Most small systems will have the ability to bypass the heat recovery element as well. I don't know which brands you might be looking at. Potentially the cheaper ones don't have the dampers in them, but a lot of them do. What about the cost effectiveness for the proposed system and products? And I guess that's a discussion that you have to have with the client as well, or with the architect when you're having that discussion. You have to define cost effective. So when you have a cost effective system, you also have to consider how often are you going to be refitting that apartment? How often are you going to have externalities in terms of black mold? Is the body corporate going to come after the developer and they're going to come after you? Cost effectiveness is thrown around in terms of material cost or equipment cost, but there are extra considerations that have to be brought in when you talk about cost effectiveness, because when you have moldy buildings, it's currently a rapid repair issue, I think, in Victoria, then that essentially is much harder to deal with. It won't happen immediately, but it might happen quickly. And so your cost effectiveness discussion has to factor that in as well. A question about from Michelle about do the HR retrofit wall mounted units have acoustic insulation to ensure excessive noise does not come through? Yes. So often the reason there's so many units suddenly available in Australia is because those units have actually been around for 15 to 20 years in Europe. And so again, they have noisy roads in Europe, and these systems have very good acoustic attenuation numbers. So the decibel ratings, for example, on some of the units off the top of my head is between 40 and 50 decibels with an option for additional silencer vents on the internal side. It's not as good as a solid concrete wall, but it's usually a bit better than the windows next to it. So you're not increasing the noise in the room by a huge amount. You will be increasing it slightly. And again, it's a trade-off whether you want to consider fresh air and noise as two separate things, whether they're competing. Noise obviously would be best if you had no windows and just a solid, big, thick concrete wall. Obviously, you'd want to make sure there's no trains or anything going past, because the concrete would reverb with low frequency. But if you have a a solid concrete wall with no windows and no fresh air, no one will want to live in that apartment. And so there's a trade-off that you have to have with every discussion there. Fresh air can be a really good selling point, and particularly for people who are renting the system, it's just a trade-off with the noise that can get through these systems. And also the noise of the fans themselves has to be considered as well. So you may go for the smallest system, which has will just scrape through in terms of airflow and effectiveness, but you will have those fans running harder and noisier for more of the time. So buying cheap does not necessarily have a good cost effectiveness when you have tenant complaints. And I think one last question in here, does the air tightness environment spread COVID quickly? So that's an interesting one. I have seen a few studies where active ventilation systems, or not active ventilation, sorry, internal heat, internal mechanical systems have spread it more quickly through the building. They do need to have specific filters, and I know there's other tech talks about the types of filters and things you can use to capture viral particles. If you're supplying fresh air into a room and then pulling it out in the same room with a retrofit system, then it doesn't spread the system around. It doesn't spread it from room to room because you're pushing and pulling in the same environment, and that's why they do often work a little bit better in leakier buildings as well. I don't know whether I covered that fully. They do have a balanced ventilation in one room, meaning that you don't spread stuff around the building. Are you aware of the average cost of a retrofit wall-mounted unit? Well, yeah, certainly. We've got them on our website. We do sell these units. They're usually on the order of $1,500 to $2,500, maybe $3,000 if you include installation. And often when there's a tenant or an owner of a building has had complaints or has to retrofit the apartment or has had to potentially put tiles down, a row of tiles next to the windows because of the large amount of condensation that's forming, you can have the small cost of the systems being a couple of grand be very, very quickly accepted by someone who's gone through that whole apartment retrofit situation where they've had to remediate or refit an apartment due to mold or condensation issues. All righty. I think that about wraps me up. A couple of minutes to spare. I can't see any other questions have come in. I don't know
I think you've pretty much covered them all. So thank you very much, James. So yeah, that does bring us to the end of today's session, everyone. I just want to start off by, of course, thanking James very much for his presentation today. And thank you all for your attendance in today's session as well. Just to let everyone know, the recording of today's presentation will be made available in about a couple of weeks' time, and I'll send you all out an email to let you know when that does become available for viewing. If you do wish to view or register for AIRAH's other upcoming technology talk or streamline sessions, you can do so via the AIRAH website, which is airah.org.au/webinars. And as always, if you can please spare a couple of minutes to fill out our survey, it is greatly appreciated and it does help us improve our service delivery. So thank you all once again. Thank you very much, James. Very engaging presentation.
Thanks for everyone. I'm glad everyone was interested and a lot of participants and a lot of questions. It was actually great. Thank you very much.
No, not a worries at all. So thanks everyone and take care.